Let's move on the next presentation. Dr. Min, the professor
Yes.
of East China Normal University, and he will present a new novel in validated loop learning framework called Trainify for developing secure deep reinforcement learning (DRL) system through paradoxical case-based abstraction and refinement. Dr. Min, please give a presentation.
Yes. Thank you very much for the invitation, and thanks very much for the introduction. Maybe I first introduce myself briefly. I'm now working at East China Normal University, but before joining ECNU, I studied and also worked in Japan for 6 years, and I'm working on formal method. I mean, how to use mathematical ways to guarantee the safety of software systems. So I got my PhD from Japan Advanced Institute of Science and Technology, and after that I worked there for 3 years, and then I returned back to China and to work in the East China Normal University. And in recent years, we are mainly focusing on how to guarantee the safety of deep reinforcement learning systems, and also keep my eyes closely on our Japanese colleges. And I know there are a lot of good works from Japan, and also attend this symposium every year. And I know like Ishikawa Sensei, so his group is now intensively working on engineerable artificial intelligence, and also they have published a very good works. So in my talk, I'm going to explain 3 parts. The first part is mainly about I will explain you how we can train and verify safe deep reinforcement learning systems based on abstraction, and I also show you how the abstraction can enable us to do some black box reachability analysis, so that is more tight and scalable than white box surveys. And also the abstraction can help us to do some analytical probability robustness verifications of the training systems. So that's the basic content of my talk. So first, I will first explain you what is deep reinforcement learning. So in my project, so we are mainly considering the AI systems that are trained by deep reinforcement learning. So this kind of technique for training a deep neural network on system states in order to learn optimal actions by interacting with the environment. As you can see from the left finger, so assume that we have an agent, right? We have an agent, so it observes the state from environment and then feed the state into the neural network, and the neural network will compute an action, and with that action, so the agent will move next step. At the same time, so the agent will get a reward according to some predefined reward function, and also the agent will update the parameters in the deep neural network in order to make sure so it will.
Dr. Min, we just want to share your screen by yourself.
You cannot see my screen?
Yeah, please share your screen.
Sorry, you cannot see my screen?
We can see your screen. So please share.
Share
by yourself.
So, okay. Now can you see my screen?
Yes, now we can see.
Okay. Sorry. Yeah. I
so,
forgot to. Yeah. Yes. So as you can see from the slide, so the left finger so show you the basic workflow of deep reinforcement learning, and we have an agent. So this agent will observe a state from environment, and then it feeds the state into the neural network right here. And this neural network will compute an action A, and the agent will apply the action in order to move forward, right? And at the same time, so the agent will get a reward from this action, and based on this reward, so the agent update the parameters in the deep neural network in order to make more optimal, best reward later. So that's a kind of workflow of deep reinforcement learning. And so the left hand part, this is actually a snapshot of applying deep reinforcement learning to train a game. And so here you can see this is a neural network, and this is the agent. And so at any moment, so we observe the state of the agent and also environment, and feed it into the neural network to compute how the agent should move, like up and down or back and forth, like that. And then the agent will get a reward from making this decision, and to update the parameters in the neural network correspondingly. So that's the basic idea of deep reinforcement learning. And as we all know, right now, so deep reinforcement learning has been applied to many safety critical domains, like self-driving cars, and also robotics manipulation, or also games, and industry automation. So we need to find a way to guarantee the safety requirement of such kind of DIL applications. So this is an example showing how we can train a DIL system. So this is a smart car problem, and this is well studied as a benchmark in DIL community. So let me first simply explain how this example shows. So in this example, we have a state which is a pair of position and velocity v, and the action A. So the car will make an action. The action is actually a real number that represents a force that is going to be imposed on the car. So the action is computed by a neural network here. So we feed a state into the neural network, and then the neural network will compute an action, so which actually a force, a real number, and then we apply this force to this car to move this car maybe back or forward, like this. So yeah, that's the basic setting of this example. And so at any moment we compute the action based on the current state, then we can compute the next step, the next state, based on these two equations. So this two equations says how the position and the velocity is changed by the force. Yeah, that's the basic example of this deep reinforcement learning application. And for this one, so after we train such kind of application, we want to make sure this application will never reach some unsafe state, or this application should satisfy some safety requirement. So there are several existing approaches for analyzing the safety of such kind of systems. So the first one is simulation. So the idea of simulation is very simple. For example, we assume that we start the system from some state S1, and then we can compute the action according to the model we have trained, like pi here. Pi is a trained neural network, and then we feed this the initial state S1 into the neural network. Then we get an action. Then we apply this action according to the equations we know to compute the next step, next state. And then we can compute the next state like this. So we will get, as you can see, this from in this finger, we can see here. So we will get a lot of passes. Giving a concrete state, we will compute a path, and this path, the set of this is passes. So formulate this like this finger, and we can guess from this finger that so the system may not reach some unsafe state. For example, if we have some unsafe state here, so we can see from this simulation that probably so the system cannot reach such unsafe state. But the limitation of simulation is very clear because it cannot cover all the cases, and it cannot determine if the systems will never reach such unsafe state. And to overcome these limitations, another approach is proposed, which is called reachability analysis. So the idea of reachability analysis is that we do not start from some concrete initial state. We start a set of initial state. So that's the basic difference from the simulation. So we first start a set. Here is S1 is a set of initial state. And then we want to compute. So what's the next set of successor state, right? So if S1 is discrete and also finite, so the problem is simple because we can enumerate every state in S1 and then compute its successor state. Then we will get a finite set of successor state, right? But the point here is S1 is usually not finite and also not discrete. It's usually a continuous infinite state space, like an interval. For example, we assume that S1 is an interval from 0 to 1. Then we cannot enumerate all possible values in this interval. And the solution is we usually over approximate so the system. For instance, we take this interval as an atomic data. Then we need to determine so what kind of actions so that the trained neural network will apply on this interval. And then we will get a set of actions, A1 here. But this A1 is actually an overestimated result. So actually there may be some actions not in this set. So that can be applied to this interval, right? And then we get an overestimated actions. Then we apply this actions, all the actions to this to S1 to compute S2. So in this way, we can compute next step, the reachable set, the reachable state in this way. But this approach has two limitations or difficulties. One is we need to compute A1 here. We need to compute the set of giving a set of system states. We need to compute the set of actions that will be applied to this set of states according to the deep neural network. But because deep neural network is a black box model, so usually it's very difficult to compute the exact set of actions. So to solve this problem, we usually need to over approximate this model and to get an overestimated result. And this may introduce a lot of over estimations. And also, we know this set of actions, and we need to apply this set of actions to the state of to a set of states, according to the system dynamics F here. But this one also introduced a lot of over estimations. So usually the traditional approach cannot reachability analysis approach, so introduce a lot too much over estimations and cannot it may produce a lot of false positives. But the good point is of reachability analysis is here is that once we can prove, as you can see from this diagram, once we can prove that so some unsafe states cannot be reached from the initial state by reachability analysis approach, then we can safely conclude that the system will never reach this dangerous state. But not vice versa, because if we find some, for example, if we find some overlaps, right? If we find here some overlaps with the dangerous state, so we cannot conclude that the system is must not be safe, because there may be some false positives that overlap may be caused by the over estimation of the reachability analysis approach. So that's actually a research topic in this for method community and also deep reinforcement learning community. They want to they are trying to solve. So basically, formally verified deep reinforcement learning systems, they are facing 3 challenges. So the challenges is because it's the system state of such systems are infinite and continuous. It's very difficult to verify completely, and also more difficult code part is so the system include an explicable AI component like deep neural network. So this is a black box model, and it's very difficult to know so what kind of actions will be taken on the state, given a state, right? And another difficulty is that such systems, so they have nonlinear system dynamics. So it's also difficult to know even we know the action, we cannot straightforwardly compute the next state according to the action, because the system dynamics is nonlinear, and usually we need to over approximate the nonlinear dynamics using linear ones. So to overcome these challenges, so our starting point is, can we ensure that a trained model always returns a unique action on all the state in S here? I mean, giving a set of state S, so can we train a model, can we train a deep neural network that will compute a unique action on all the state in S? So that's our starting point. If we can do that, then we know we only have one action A on all the state in this set, right? Then we don't need to consider the deep neural network, because we know the action is A. Then we can compute the successor state S prime according to A, and also system dynamics F here. So that's our starting point. We want to train a model high here that can always return a unique action for given set of system states. So here is our basic idea. So basically, for the existing approaches, so when we train a system, right, we take a concrete state from the state space, right, and then feed this concrete state or actual state into neural network and to compute an action. But our approach is that before training the system, we discretize the state space into several non-overlapped set of states. Here, like you can see, this one is a kind of a unique, or it's kind of atomic state space. So we consider all the states in this set. So they are in the equivalence class, right? And then we feed this discretized state, or we call it abstract state, as a whole into a neural network to compute an action. So in this way, we know for each set, we know there is a unique action, right? A1, A2, A3. And then we can compute the successor state according to this action without knowing the internal settings of this model. So in this way, we can treat this deep neural network as a black box model. So based on this one, we propose a framework, a new framework that include training, verification, and refinement. These are 3 steps as a loop. So in this loop, we for each loop, we train the system. We train the system in the first step based on our abstraction ways. And then after we train this system, then we can construct an abstract model that we can model check. Then in the verification phase, we can model check the system if the system satisfies some predefined properties that is formulated by some ACTL formula. Then if we verified this model satisfy the formula or the system, it's usually a safety requirement. If we can verify this model satisfies the requirement, then we know the system we trained so meet our requirement. Otherwise, we will get some counterexample. So by this counterexample, we will refine the abstract state. We will refine the abstract state into some smaller ones. Then we repeat the training again to train on its refined state to get a more accurate or more to get a finer models, to get a finer deep neural network. Then after we train and get the finer deep neural network, then we do verification again until we can model check all the predefined requirement are satisfied by the model, by the system, by the training system. So that's a basic the framework for our approach. So I will show you step by step how it works. So first, assume that we have a state space. In this state, we have 2 dimensions. One is the velocity, and the other is the position. So this is the original state space. Then we discretize this state space into several interval boxes, like you can see on the right-hand side here. So in this discretized state space, we want to have 16, right? Abstract state. No, it should be 20 here. So we have this 20 abstract state. For example, assume that the variable v, the range of the variable v is -1 to 1, and then we discretize into several intervals, right? And for each interval, this kind of it's considered as a whole, as a unique representation of all the states in this interval. And then we need to figure out how we can feed the intervals of the abstract state, this one, So as a whole into the neural network. So here is how we do it. So originally we only need to feed the actual value of P and V into the neural network. So we only need to two input neurons to get this values, input values. But because we need to input the interval of each variable, right? And then we double the input neurons here. And for each neuron, it gets the extreme values of the interval. For example, if we know P is 0.5 and it belongs to 0.4 to 0.6, this interval, then instead of feeding this 0.5 into neural network, then we feed the extreme value of the interval here, 0.4 and 0.6 into the neural network in order to compute a concrete action here. So in this way, we can guarantee that all the values, right, in this interval will have a unique action A here. And based on this, after we train the system based on this setting, and then we will obtain a trained system, right? And then we also can build a character structure. Character structure is a mathematical model that is well studied in the model checking community for verify some temporal properties. So character structure, you can consider this is a kind of state transition system. So the basic idea is giving a set of state as here, then we feed this because our model, our deep neural network is trained on this kind of abstract state. Then we can feed this abstract state into the neural network to compute an action A here. And then we apply this action A to this set of state, to the abstract state S by according to the equations defined for the dynamic state, dynamic system dynamics. Then we will get an overestimated reachable set of states here, and then we will based on this set of states, we will check so all the abstract state that have an overlap with this set of states. For the instance, here we have S1, S2, S3, S4. So this 4 abstract state has an overlap with this set of states. Then we see that there is a state transition from S to S1 and S to S2 and S to S3 here, S4, S3, S4 like this. So in this way, we can build a state transition system, and we use character structure to represent this state transition system. And after we build this model, then we can model check whether this model satisfies some predefined safety requirement. If we can verify, then we are done, right? If we cannot model check it, that is the current model doesn't satisfy the property, then we will get a counter example. So during the model checking, we need to do some more abstractions based on the properties. So I will skip this technical part. So you can see my papers if you are interested in the details. So if we can model check the system satisfy the requirements, we are done. But if we cannot, then we will get a counterexample. So based on this counterexample, we are going to refine our abstract state space. For example, if we know there is a counterexample occurring on this in this state, So we will split this state into two final states. For example, we split the state according to the variable p here, and then this interval is split into two, right? And so apparently, so this two abstract state is finer than this one, right? And then we train the system. We train the system again based on the refined system state in order to get a more optimal deep neural network. Then we do verification again until we can finally verify all the system, all the predefined safety systems satisfy the properties, right? So in this approach, so we can train a system that satisfy all the predefined safety requirement. So there are several novelties in our approach. For example, so because in our approach we introduce verification into the training phase, so we call it verification in the loop training. And by verification, we can detect the errors earlier during the training, and then we can guide the training based on the verification result. So in this way, we provide more reliable guarantees if we train and finally we train and verify the system. And also you can perceive this kind of approach is a requirement-driven training, because we first have some safety requirement, and during training we verify whether the requirement can be satisfied or not by the current training model. And if not, we continue to train and based on the verification result. So this can be perceived as a requirement-driven training. And another novelty is that because we can do verification in the training phase, because we introduce abstraction to the system state, and then we transform the infinite state space into finite state space, and based on this finite state space, so it makes the verification part easier. So we also find that this abstraction-based training can help us produce more robust systems. So later I'm going to show you why. So in this way, we can develop more robust systems. So so we also can apply reachability analysis to the systems that are trained using our abstraction-based way. So as I have explained before, the existing reachability analysis approaches rely on computing the set of actions for a set of actions according to the trained model, trained deep neural network, for a given set of system state in order to compute the successor state. But this, because we need to over approximate this deep neural network, then we introduce over estimations to the action. So, but our approach, so because we can feed this set of system state as a unique data into the model, right? And compute a unique action. So this step will not introduce any over approximations. So in this way, we can compute a tighter success state. So this success state is tighter and more close to the actual success state of the previous state space. And so this is a workflow of how we can compute the successor state of a set of system state based on the trained model. For example, we have assume that we have this set of state, and we want to compute the successor state of this set of states, right? So how could we do it? So first we discretize this state according to the abstract state we have used for training the deep neural network like this, because here this set of state has so can be discretized into 4 parts. So this 4 part is determined by the abstract state. So we used for training the model, and then for each sub-state, abstract state, we compute its action according. We feed this one into the neural network in order to compute a unique action. Then, according to this action, we compute its successor state here, and other substate are the same. After we compute all the successor state space, then we do some unification, right? We do some unification to unify two overlapped sets, and then compute again for its successor state in this way. So this is the basic idea, and this approach has some advantages. One is it's general because it is applicable to any types of AI models, because we treat the AI model as a black box. And also, of course, it is scalable because it doesn't care about the internal settings of like the size of neural network, and also activation functions, and also architectures. And also, more importantly, it does not introduce any over-estimation in order to compute the actions for the system state. So our approach is tight, and it can compute a tight successor state. So that's the advantages of our approach. And another point is that so we can formally analyze the probability of robustness of the system. So what is the robustness? Assume that you can imagine that we apply some noise to a system state, because in the open environment the noise is very common. For example, if the state actual value is 0.5, and we may, so this value may be perturbed by some environment element, right? And so this value may be changed into for 0.51 like this. So the system will not, the model will not make decisions on the exact value, but on the perturbed value. So we want to make sure after the system state is perturbed, and we want to make sure, so what's the, we want to know what's the probability of we can still get the optimal action or optimal performance of the system, even if the system work on some noisy environment. So based on this abstraction, we can get analytical probability of the robustness. So here is how it works. For example, if given a concrete state S here, if we know after we apply some noise to this state, we know all the possible perturbed states still belong to the abstract state here, because we know in this abstract state, so it has a unique action A, and we also know a concrete state, the perturbed state of the concrete state will not exceed the range of this abstract state. So of course, so after this state is perturbed, so the trained model will still produce the same action A, right? So the probability of being robustness is 100%, right? So if the concurrent state here is on the probably on the edge of the abstract state, then there is 50%, right? 50% the perturbed state still belong to the abstract state. Yeah, for in this case we have 50% probability of having the optimal action. And another extreme case is so the actual state is at the corner of the abstract state. So in this case, we have 25% possibilities of being robust. So that's how we can compute the probability of a system to be robust, even under some perturbations. So here is a theorem saying that given an abstract state deep reinforcement learning system, so the state abstraction function is defined, then we can determine the lower bound of the robust probability of this system. So it increases monotonically with the abstraction granularity of the function. So intuitively, so if the abstraction granularity is big, then the robust probability are also big. So we did several experiments on 6 classic control problems like Monte Carlo, pendulum, and catapult. So and taller like this. So they are very classical control problems well used in deep reinforcement learning community. And we specify the requirement, the safety requirement of each example as ACTL formulas. And we want to train such systems that can satisfy all the predefined properties like this. And then with this some experiment, we trained the system in our approach and also in conventional DRL algorithms. So as you can see here, there are some time overhead because of the verification compared with the conditional ones. But the more important part is that the system trained in our approach will never cause any violation to the properties, to the safety properties. But the system trained in conventional algorithms, so we find some violations to the safety requirements. And also we also compare our reachability analysis approach with some state-of-the-art reachability analysis that are designed for deep reinforcement learning system like VeriSig and ReachNN. And as you can see here, so using our approach, we can compute more tight. Here, this is the execution traces, so it's more tight than other two tools. And here, this is more detailed experimental results. I'm not going to much details on that. So you can see the document, technical document. So if you are interested, and also we test the robustness of the systems trained using our approach and also using the conventional approach. So we found that so our approach is under the same perturbations or same noise environment. So our approach so can have a better performance than the traditional ones. So to conclude, we found that so abstraction is a very good way to how to say, it's a good way to connect formal method and also deep reinforcement learning. As all the formal method people know, so in order to model track complex systems, we really need to introduce abstraction to make the model simpler and easier to verify. And in this work, we found that abstraction is also good for training an AI system, and then which can contribute to formal verification and also to developing more safe and robust AI systems. So we think that so abstraction is a nice solution to compute to integrate this to communities for some new training approaches and also new formal verification approaches. So yeah, that's my all the talk all the content of my talk. So if you are interested in this approach, and you can see more details in from the papers we have recently published. So that's all for my talk. Thank you. Sorry, I have used 5 minutes more. Okay.
Thank you, Dr. Mi. It's a good time to yeah. So maybe this is no time to
sorry. Yeah.
Question. Yeah, but if you have any question, please put in the chat.
Yeah.
Maybe Dr. Mi may also reply to in chat through the chat. Yes.
Yes. Okay.
Yes. So thank you for a good presentation, and maybe let's take a break. It's okay.
Yeah. Yes. Thank you.
午後はですね、1時30分から、始まりますが、15分前に、オープンします。で、それまで一旦このサイト、アドレスのチャット、アドレス一旦閉じますので、ちょっと一度ご退席いただければなと思います。1時13分にもう一回開局いたしますので、よろしくお願いいたします。じゃあ、昼休みにしたいと思います。ありがとうございました。
ハローさん。あれ、み先生いますまだ。I want to talk to you.
Yeah. Thank you so much.
Thank you so much. It's very interesting talk, and especially I'm very interested in the requirement-based training because and also you surprised me because you got a PhD from Ogata Sensei. Because I'm also OB of Katayama Sensei, who was the president of Agilist.
Yeah, I know that.
Yeah. And I have one question. Your counter example framework of abstraction method, it can be applied not only reinforcement learning, but also general neural network based learning. Do you have any comment on that?
Yes, that's a good question. And also we have tried that we can maybe for the like image classification, right? And we can first do some abstraction to the images before we feed it into neural network. I mean, so we first do some abstraction, apply some abstraction, and not we do not input each value of the pixel value into neural network. Instead, we want to input the an interval of the pixel. For example, because we can apply some noise to an image, right? So the effect of the noise is to change the concrete value of each pixel into an interval. And then if we can feed this interval into neural network, then we can clear such kind of noise in order to make the neural network more robust. Yeah, that's our observation. Yeah, we also did some experiment, and we found that the network trained in this approach has better performance. Yeah, than trained on concrete images.
Very interesting. Okay, thank you. Thank you.
And also we found, so 20 years ago, there are some studies trying to train interval neural network. Yeah, interval neural network. Yeah, the input is not a Kinker value, it's an interval.
Interval.
And yeah, it shows there are some advantages of such model. Yeah. So our group now is focusing on this area.
Oh yeah, very interesting. Yeah, research. Yeah, thank you. Thank you.